Thank you very much for inviting me. This has been a terrific workshop. I have the unenviable task of being the last person to talk, but I'm actually incredibly grateful for it because I was a last-minute inclusion here. Since I'm the last talk of the day, I will put in lots of cute videos of children playing as much as I can to try to keep everyone here and awake. And I want to begin with what we all know, which is there are a lot of reasons we learn. We learn to get rewards and avoid punishment. We learn because we can't help it. Because if there's structure in the environment and we're the kind of organism that can detect that structure, we will represent it. And even young infants will pick up statistical properties of the environment, even from just, for instance, a few minutes of passive exposure to statistically structured syllables. But the reason we're all here and what we care about in this workshop mainly is epistemic curiosity, so curiosity in order to gain information. And I think I'm also appropriate as maybe an edge talk because I'm going to talk really about higher order cognition, about the kind of epistemic curiosity that we think goes into inquiry and discovery, but I'm going to talk about in very, very simple cases. When we think about how children learn, we think very much of them being naturally curious, naturally playful. There's probably no more uncontroversial statement that I can make than this. Everyone thinks that children learn by doing, children learn by exploring. Parents, educators, and researchers, if you do a Google image search, it comes up basically everywhere. It's essentially axiomatic. But it's a little bit problematic because there's actually very little evidence for systematic patterns in children's exploratory behavior. In fact, if you look at science education research, there's considerable evidence that children are poor at some kinds of learning from behavior. And prima facie, there would seem to be a very large gap between formal theories of learning and the behavior of what many of us think are maybe our most powerful learners, which is very young children. So part of my research program has been trying to bridge what in some cases looks like an almost insurmountable gap. And the only way to do that, of course, is to pick out just very tiny components of the full richness of play. And I'm gonna come back to that at the end. So we go from something that's essentially uncontroversial to, I think, this very sage statement by E.O. Wilson, which basically says there's no behavioral concept that's been more ill-defined, elusive, and controversial, and also unfashionable than play. So that's what I'm going to try to take on here a little bit. And I'm going to talk effectively about rational exploratory play. This is the only math I'm going to put on the screen, although in fact many of the things I'm going to show can and have been formally modeled by my colleagues. But for my purposes, the very simple claim is this. If play does support learning, right, if some aspect of what children are doing supports learning, then children should at least selectively explore in some cases where evidence fails to distinguish competing hypotheses. And what this very simple equation, Bayes' law, as most of you know, makes really clear is why there are two cases where that should happen. It should happen either because evidence is surprising, which can happen because evidence is more consistent with one hypothesis than the other, but you initially believe the other one, right? So that's a case of surprise. But it can also happen because evidence is confounded. So the evidence is equally consistent with two hypotheses that you thought were approximately equally likely beforehand, right? So in both of these cases, we expect, if you are sensitive to the ambiguity between the hypotheses, those might be cases where you want to engage in exploration. There is a lot more to be said, much of which has been said at this meeting. So let me just lay out a few things that I do know, but may not be represented in these experiments. First of all, I do focus on high-level epistemic curiosity because I'm interested in how children go on to develop a rich common sense understanding of the world. But of course, we're curious about all of the things mentioned here and also many things that haven't been mentioned here, things like gossip or particular threats. I focus on curiosity because I've been interested in the relationship between play and learning. But a focus on play causes you to do two things. One is to just focus on intrinsic rewards. So I tend to match extrinsic rewards. Many of my toys beep and light up and do things, but it will do that equally well across both conditions. I'm interested, like most people here, in the intrinsic rewards of information gain. It also causes me to do something that has been less done here, which is to assume negligible costs. right? Because although I think we heard from one speaker that mistakes are not forgiven, in play, mistakes are roughly forgiven, right? They're very low cost things, both in terms of opportunity costs. You're being taken care of by presumption, you're being fed, you're being sheltered, therefore you have the luxury to do this. And also in terms of actual costs, some minimal energetic costs, but very little else. But of course, costs and extrinsic rewards have profound effects on actual exploratory behavior. And that affects things including thinking. I said hypotheses intention, right? But it really matters how many hypotheses intention, right? If it's just two, and a simple action can disambiguate them, that's a very simple case. But if your entropy over hypotheses is very broad, it could be one of 17 hypotheses, that's going to be very costly to disambiguate. You should explore less. So I'm focusing here on sort of really, really simple cases where I can minimize costs, match extrinsic rewards, and see if in those conditions children are sensitive to epistemic uncertainty. So most of this is actually fairly old work. I'm revisiting it mainly for the conference, so I'm going to start by talking about that, and then I'll end with a few newer ideas. So the claim is basically this. If play and learning are related, then children should be curious. They should selectively engage in exploratory play when evidence fails to distinguish competing hypotheses, either because the evidence supports an otherwise improbable hypothesis, the evidence is surprising, or because it provides equivalent support for multiple plausible hypotheses, so the evidence is confounded. But in addition to that, if children are not just going towards cases where there's possibility of information gain, but they are really sensitive in how they are exploring, then they could learn potentially just by exploring randomly, just by going to that space and doing a lot of things. But what they might do is they might be particularly sensitive to those kinds of interventions that are most likely to be informative, and they should prefer informative actions in that space to just random exploration of the space. So that's what I'll talk about there. At the end, I'm going to talk briefly about some new data, something we may all be curious about, which is, do individual differences in exploratory behavior relate to intelligence? Is one of your monkeys smarter than the other? Now, in that case, you tricked the monkey, and it might be smarter the other way. But here we're going to assume there's a positive relationship between exploration and intelligence, or at least ask that question. And at the very end, if I have time, I'll speculate about what I'm actually most interested in now, which is a little bit about why human beings have such a range of events that we are curious about. We're all here dedicated to understanding the mind. There are whole meetings and conventions and activities happening out there where people would be deeply uninterested in everything we're doing here, but are fascinated by things that would be deeply boring to us. And why the range? So let me see how much of this I can actually get through. I'm going to start with an incredibly simple study. Of course, we all think you should explore when evidence is surprising. And in some sense, the point of this study is just to point out something we know but whose effects can be surprisingly subtle, which is what counts as surprising depends on your prior beliefs. And if you're a human child, it's really the representation. In some sense, it can be not just, at least as far as we know, specific exposure to differential evidence, but how you represent those relations. So I'm going to show you how that works here. A very simple task. And it's a task borrowed from Inhelder and Piaget from a long time ago. I'm sorry, actually, Annette Karmeloff-Smith and Inhelder. And they wrote a classic paper called If You Want to Get Ahead, Get a Theory. And they pointed out that young children are perfectly good at balancing blocks proprioceptively. If you hand them blocks, they can balance them by feel. But if you ask children to make predictions about where blocks will balance, young children will tell you it's going to balance in the geometric center of the block, right? Which is a very good strategy for symmetric blocks and obviously a disastrous one for these asymmetric blocks. These same children, if you ask them to close their eyes, will have no problem balancing the blocks, but if you ask them to predict, they will go for the geometric center, and it's only later that they will go towards the center of mass. And of course, the youngest children actually don't make predictions about what blocks are balanced. They'll just do it proprioceptively. So we took advantage of this. We asked kids, okay, well, where would you put this block on this balance if you wanted to make it up? They didn't get to try it. They just had to point. And across 3 trials, we identified kids who were systematically one way or the other. They either had a kind of slightly more adult-like theory. It's too rich to call them mass theorists, but they knew that they needed to compensate for the position of the heavier block. And center theorists who really went right with the geometric center. And the main thing I want you to notice about this slide is these kids are about the same age. You wouldn't be able to tell them apart by looking. They could be in the same classroom. But they have really different theories about how this world is going to work. Having shown them that, we familiarized them with an asymmetric block. We let them play with it for a while. And then we just set up an exploration task. So we put the block they had just explored up onto a balance, and then we brought out a brand new novel toy. And we wanted to ask what the kids would do when we walked away and let them play. And the prediction here, of course, is that this is a completely unsurprising evidence for a mass theorist, but it's surprising for a center theorist. So rather than showing a novelty preference, although these are slightly younger children, they should go back and explore this block, whereas the mass theorist should do the other thing. Now, because we're at MIT and we can be really clever, we can develop a block that actually does balance in the geometric center because we have a magnet in there. And so we could also set it up in the reverse way, and this time we predict these kids are going to selectively show the preference and play over here. And it's an important point that there's actually a magnet in both conditions, and I'll get to that in a minute. But this is how it's set up, and we let the children play. And indeed, we got the predicted effects on kids' exploratory play. So again, these are all roughly the same age kids. But what you'll see is that when center theorists saw a block balancing in the geometric center, they tended to play more with the novel toy, whereas the mass theorists played with the balance. But when that block was balanced over the center of mass, the mass theorists tended to play with the novel toy, and the center theorists went ahead and played with the balancing block. So you switched their exploration preferences depending on what their prior beliefs were. All the children, as you'll notice from this graph, spent some time playing with those blocks. And if they did, they found the magnet, right? Which accounts for some of the extended play there because they could find that magnet. So you can also then follow up and say, well, what did they do with that magnet? Because in every single case, if you say, why is that staying up there? The magnet's a perfectly good explanation, right? It's a sufficient explanation in all cases. But if the children are like us, what you might expect is they selectively refer to extraneous variables when they get evidence that's anomalous with respect to their theories. And so we thought children might be more likely to appeal to the magnet when the evidence conflicts with their theories rather than when it confirms their theories. So we asked the kids, what makes the block stay up like this? And when the block was positioned in the center, 67% of the mass theorists said the magnet. The center theorists basically never did. And when you asked about the mass, then the center theorists appealed to the magnet, and the mass theorists were less likely to do so. You could ask what that means for curiosity more broadly, but we'll leave that one for a moment. Yeah?
Were they asked after they played with it?
Yeah, this is the end. They've done all of their play. This is at the end. Okay. This is a very simple violation of kids' beliefs. It's kids' beliefs about the physical world and something with which they have a lot of experience. But you can ask about violations of expectation on many, many different levels of abstraction. So I'm actually going to return to some study I did for my dissertation work, believe it or not, because I think it might be interesting in this context. And I'm going to ask about a violation of a more abstract principle. And it's a principle that Simon Laplace articulated very nicely. He said, if there were an intelligence knowing all the forces acting in nature, and its intellect were sufficiently powerful to subject all data to analysis, to it nothing would be uncertain, right? And this is a statement of strong determinism. Right? This is appropriate to 18th century thinking, and they believed if you could just know everything, there wouldn't be anything left to know. Now, we don't believe that statement is true in this era of quantum uncertainty, but it could be a rich part of our intuitive theories about the world. And it has an important relationship to exploration because the assumption here is that causes only appear to act probabilistically because there are unobserved latent causes, because there are things you do not know about the world. And if children believe something like this, then when effects occur probabilistically, they should assume unobserved causes are present. They should selectively explore. Particularly, they should assume either a necessary generative cause is missing if an effect doesn't occur all the time, or a sufficient inhibitory cause is present. In this experiment, we just asked whether children did this. And here's the structure. The children either got a probabilistic causation condition when effect occurred only on the second and sixth trial of 8 trials, or a deterministic condition where the effect always occurred. So I'm going to show you what it looked like in the probabilistic case, and here's the setup. The children, maybe? The children see that there's a ring on the, whoops, hang on, we need to go back one slide. Maybe. All right, well, the children see that there is a ring on the toy, and if you flip the switch, then the toy lights up, which is showing up on my screen but not on yours. Aha, there it is. There's a ring on a toy. If you flip the switch, the toy lights up. And the kids see that a bunch of times, and then you show them a way to stop that effect. You say, look, if you take away the ring, then the toy won't light up. Okay? So all the kids know now how to make the toy go and how to make the toy stop, and this is perfectly deterministic for all the kids. And at this point, I hand the switch to a confederate, and in the deterministic condition, the confederate does the same thing. The toy always works. In the probabilistic condition, sometimes the switch works, and sometimes it doesn't, for no apparent reason, right? At the end, I open my hand. I have a little keychain flashlight in there, but the kids don't know it's a flashlight. They've never seen it associated with the toy. They've never seen it at all until then. I just set it down, and I say, okay, I'm going to take this back. I'm going to flip the switch. Can you make it so the toy won't work and the toy won't light up? And the important point is the kids know how to do this. They've already seen how to do this. You could just take away the ring. So if you want to exploit your knowledge, you can perfectly control this by doing what you have already done and what you see. And if you're just attracted to novelty, then in both cases, the deterministic case and the probabilistic case, you could explore this brand new thing that I set out there. But of course, the prediction is that only in the probabilistic case, where you're looking for some latent unobserved cause, well, here's something that was plausible insofar as it has an affordance and it was hidden in my hand. And in that case, if you believe that there might be an unobserved cause, you might explore, you might selectively pick up this thing you've never seen and try to use it to stop the toy. And in fact, those were the results almost overwhelmingly. The kids in the probabilistic condition picked up that toy, tried to use it to stop the toy. The kids in the deterministic condition almost never did this. They preferred useless information here, right, effectively. Useless in quotes, because of course we think in the real world this information might be incredibly useful. But here they had another cause, they had another way of generating the outcome. Importantly, kids make the trade-offs as well. I won't show you the data, but if they know that in a potential cause is missing, then they go ahead and do not explore. So if they knew that the plug was loose, sorry, that should be a generative cause, then they don't go ahead and treat the flashlight as if it were causing the effect, if they know that the switch might have been loose on the other cases. The reason I'm dwelling on this just for a minute is I think children are massively worse than cockatoos at some of the things that Alex showed. I don't think that children necessarily have very rich or good intuitions about the physical and material structure of the world. It takes them a long time to learn how to use a pencil or to tie their shoes and to do lots of these properties. I think they would struggle a lot with that lock combination. But I do wonder about this. I do wonder, one of the things that you could do is just learn the probabilities, right? You could just learn this thing works 80% of the time and be very happy with that result. Humans aren't. We think if something works 80% of the time, we want to know why it didn't work 100, what the unobserved cause is, and search for that latent structure. And I'm wondering to what extent we think that other species, and Sam has actually some interesting evidence about possibly assuming latent structure in the sense of context or other things. But it's an interesting question whether it motivates exploration, whether it's a sufficiently strong assumption that instead of exploiting available information, if there were a really plausible salient option there, if other animals would explore for it. Okay. So this is the context where you explore because evidence is surprising and it violates your expectation. But you might also selectively explore because evidence is ambiguous, right? Because there's two causal hypotheses, their intention, you can't tell them apart. I'm going to show you how we did this. We just gave kids a very simple case of confounded evidence. If you push down these two levers, two toys pop up in the middle, and they're spatiotemporally ambiguous, and you push them down at the same time, so you don't know if this lever made them both go, or this lever did, or this one caused this one, or this one caused this one. It's a simple toy, but they're myriad causal possibilities. That's the case of confounded evidence. You could also give them strong inductive evidence. Children can learn from one trial. But just by isolating the variables about how this toy actually works, you push down one lever and this toy pops up. You push down the other lever and this toy pops up. And now you think you have unambiguous evidence. You know how the toy works. So we can give children either confounded or unconfounded evidence about the toy. We can then do what we did in the balance beam experiment, take that toy away, bring it back out along with a brand new toy, and we can ask if we can reduce, as our children, it's a new toy, we can ask if we can reduce kids' novelty preference because they are exploring this ambiguous situation where they don't know which switch makes the toy go. So I'll show you some cute children videos now. Here's a child who's going to get unconfounded, unambiguous evidence about the toy.
Push down on your lever, and I'll push down on mine at the same time, okay? I want to say 1, 2, 3, up, then we'll both bring them up. Okay? Ready? 1, 2, 3, down. Cool. 1, 2, 3, up. Let's do it again. Ready? 1, 2, 3, down. 1, 2, 3, up. Cool. Let's do it where we take turns. You go ahead and you go by yourself on your lever first. Go ahead. 1, 2, 3, your turn. 1, 2, 3, up. Cool. And now it's my turn. Ready? 1, 2, 3, my turn. 1, 2, 3, down. All right. Well, back there. I'm just right here. You go ahead and play with whatever you want for a minute, okay?
And the child shows a novelty preference, so we haven't contributed much to the field, but we got lucky this time. This is this child's identical twin, and he got confounded evidence about the toy.
Say 1, 2, 3, go, then we're going to both push our levers down. I'm going to say 1, 2, 3, up, we'll bring it back up. Okay, ready? 1, 2, 3, down. 1, 2, 3, up. Cool, let's do it again, ready? 1, 2, 3, down. Cool, 1, 2, 3, up. Let's do it one more time, ready? 1, 2, 3, down. 1, 2, 3, up. All right, let's put that and this right here, okay? And I'm gonna write something down for a minute. All right, go ahead and play with whatever you want.
All right, so we didn't just look at the first reach. Of course, we looked at their playtime over the whole course of events. And there's a lot of things you want to unconfound, like the child's chance to play with the toy all by themselves. You might want to take that away even in the unconfounded condition. And you want to control for the number of times they see the effects and the trials in separate conditions. But the short story is very simple. Anytime the kids get unconfounded evidence, they show a novelty preference. Their average playtime favors the new toy. Individual children show that preference. And their first reach is almost always to the new toy, but not in the confounded condition. They're sensitive to the possibility that there's more information to be gained. They'll override the novelty preference in this case and go back and selectively explore the ambiguous toy. Now, what do they do with that toy when they get it? Well, they talk to the ducks, they put it on their head, they reach in, they do all kinds of things. 75% of the kids also isolated the variables, but we were very careful in that paper to say, even if you don't know exactly what to explore, if you go where there's uncertainty, if you go where there's information to be gained, and you do a bunch of things, you're more likely to learn. In an environment where there are places you shouldn't bother exploring because you have complete knowledge, you should go to the places where there's uncertainty and do things, and maybe you'll find something out. But in the next couple experiments, I want to suggest that children are more sophisticated than that, that they don't always just go and play. That in simple contexts, they can select and design informative interventions that are specifically likely to get them information. Okay, so this is an experiment. Many of you have seen these little snap together beads that you can give babies or young children. You pull them apart, you snap them together. We use these as stimuli. We painted them so they're each unique. And we're going to give children different information about them. In one case, every bead you put on this toy makes the toy play music. So all the beads work. In the other condition, only some of the beads work, and they're all unique, so you don't know why. But some beads work and some beads do not work. And that's all we vary between the conditions, is just the base rate of the candidate causes here. What we do next is we take all of these toys away, and we show the children pairs of beads. And one pair is stuck together. It's epoxied together. We can't take it apart. The kids can't take it apart. We all know that. And the other pair is an ordinary snap-apart bead. But we leave it snapped together, and we put each pair as a pair on the toy, and everything works. Right? Both toys make the toy go. In principle, evidence in both these cases is confounded. It could be this bead or that bead or this bead or that bead makes the toy go. But if your base rate information is that every single cause works, there's not a lot of information to be gained here. You should assume that all of these beads work as well. And in that case, you might expect that if we walk away, the kids will play indiscriminately. But in the some beads condition, there's real uncertainty. Only some beads work. Maybe it's this one, maybe it's this one, maybe it's this one. You do not know. If kids are sensitive to the probability of information gain, but also sensitive to the fact that only one of these bead pairs has the right affordances to find out. Only one of these bead pairs could you actually isolate the variables and learn something. Then in this condition, children should selectively play with the separable pair of beads. Because in that case, they can take one bead at a time, try it on the toy, and find out if the first one works, if the second one works, or if they both do. That's what we looked for. And in the all beads condition, kids basically never snapped apart the separable beads. Only one child did that. In the some beads condition, about half the kids did. They took the beads apart and they did the exhaustive intervention, taking the beads and setting them one at a time on the toy. That was nice, but my graduate student at the time said the children are doing something interesting even with the stuck together beads, and we should try it with just the stuck together beads. And I said, what can they do with the stuck together beads? They're stuck. There's nothing you can do with them. And she said, well, let's try it again anyhow. So we gave them the same base rate for a new group of kids. One kid's in the all bead group is in the all beads condition. Another group of kids learns that only some of the beads work. This time we just give them the stuck pair. We put it on the toy. The toy makes music, and let me show you what a child did here. And I would like to try to advance this. Let's see.
This one makes a machine gun. This one.
I'll skip ahead to where the child gets the bead herself, and I hope you guys can see back there. I know the light's red on the screen, but she'll go ahead and play. And she plays. And then she does something we'd never done, and she hadn't seen before, which is she tips the beads and she rotates them so that just one bead makes contact with the toy at a time. And if you have a contact theory of causality, which is pretty good folk physics, then this is a very good way of isolating your variables that the PI on this study hadn't thought of. And so that's what we ended up coding for. And this kind of behavior, which again, they'd never seen themselves. And again, we didn't see kids do that in the all beads condition, but we saw about half the kids do that in the some beads condition. So consistent with their folk theory of what makes the toy go, they not only selected an informative intervention, they designed an informative intervention that might isolate the variables and support information gain. So they're using information about base rates to distinguish the ambiguity of the causes, and then they're selecting and designing potentially informative interventions to isolate the causal variables. Jacqueline.
Okay, but so this in a sense could be interpreted to mean that the kids, they don't really want information per se. They want to make the toy play.
Exactly not.
They have, right? So they're motivated to investigate when it doesn't work all the time.
No, not in this case.
Why wouldn't they investigate?
Sorry.
100%? Yeah.
Sorry.
I mean,
the kids can always make the point actually for every one of these experiments, and I should have made this point earlier, is that the kids can make the toy go every single time. It's a stuck together pair of beads. You put it on the way we put it on, that toy will always work. In the training, they learned that some beads work and some beads didn't, but all those beads are taken away now, right? And even there, they could always choose the effective beads, right? There's only 4. They could choose the ones that work. But after the training, this toy deterministically works. If you put that bead on the toy, it will always work. They're not exploring to make the toy go, they're exploring to find out. Now, in the fullness of time, if they encountered this toy again, would it potentially be useful to know which bead made the toy go? Sure. But for these kids, individually, there's zero benefit.
right. I was referring more to the all beads work case in which they didn't investigate. Right, so you think that means...
In both cases, the kids have a working set of beads that they can always make the toy go. Again, it's sort of useless information. They're exploring not to make something happen, but to find out how, and to find out why. Okay. I want to show you a new study. Interventions can be uninformative because they fail to isolate variables. We all know that, right? They can be confounded in various ways. But interventions can also be informative because even though they isolate variables in principle, their outcomes are very hard to distinguish, and you can't tell them apart. So I just want you to imagine, for instance, you go to the doctor, and a doctor says it's very serious. You could have a terrible, terrible disease, or you might have this very mild disease. So I'll tell you what, we're going to do a test. We're going to go ahead and put some tissue samples into this vial, and if the disease is terrible, the vial is going to turn red, and we're going to do massively invasive treatment. And if the disease is mild, the vial is going to turn maroon, and you can just go home. It'll take care of itself. Okay, so how many of you would be really, really eager about that test? You really better trust your lab technician, right, to make this discrimination. And if I told you, here's another test also we could do. It's called the X assay, and it's going to do exactly the same thing. But if it's terrible, the vial is going to turn red, and if it's mild, it's going to turn blue. How many of you would prefer the second assay to the first assay? All else being equal, probably everyone. This is a case where, again, in principle, the interventions are unconfounded, but you should, if you care about information gain, you should be sensitive to the relative discriminability of the evidence that you're going to get. And so we wanted to ask whether children were also sensitive to this. And note that to do this requires something that we're calling an intuitive psychophysics. You have to be able to know what you're going to be able to discriminate in order to plan effective interventions. You're going to need to know in advance, in some cases, what is likely to be more discriminable and what isn't in order to choose informative interventions. That's what we did here. We did it first in a dead simple case. So in this case, the children see there's a shiny pencil. It doesn't look very shiny in the screen, but it's holograms. The children really want it. It's full of rainbows. Or a beanbag. Or a shiny pencil or a very boring pencil. Okay? And we tell the children, okay, well, we're going to put one of these two into this box, and we're going to put one of these two into this box, okay? And now we're going to go ahead and shake each box, and you don't know what's in there, so let's shake this box. Oh, boom, 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 it sounds like a pencil. We shake this box. Oh, boom, 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 it sounds like a pencil. Which box do you want to open? So in this case, if the children are sensitive to the discriminability of the evidence, they should prefer this box where the pencil's easily discriminable from the beanbag to this box, even though they make exactly the same sound, even though they hear exactly the same thing. You can also do a harder test. You can say, here are some really beautiful colored marbles. Here, and there are 8 really beautiful colored marbles. Here are 2 really boring white marbles. And here are 8 beautiful colored marbles, and here are 6 really boring white marbles. We're going to go ahead and put one of these 2 into this box, all of them together, boom, the whole vial. And we're going to put one of these 2 into this box. We shake each box. I'm going to show you what this looks like. Actually, let me just make sure that the prediction's straight. I'm going to show you what it looks like. But clearly in this case, if you hear a lot of marbles, you should prefer this one, where 8 is more discriminable from 2 than this case, where 8 might be hard to discriminate from 6. And so that's what I'm going to show you here.
Well, you see these marbles right here? White ones. These are fun. Oh, 6 of my marbles. Yay! Oh, 2 of my marbles. Guess what, Taylor? These marbles with lots of different colors. Those are yours for right now. That's pretty cool, right? Marbles. That's awesome. And in this game, I'm going to hide either your marbles or Bunny's marbles inside of this box. And then I'm going to hide either your or Bunny's marbles inside of this box. Does that sound like fun? And then we're going to look for your marbles, okay? If you find them, you get another sticker. Alright, so I'm going to put Bunny right here, and we're going to do the hiding. So first, I'm going to choose either your marbles or Bunny's marbles. Here. Okay, I'm going to pour them in. Look, somebody's marbles are in here. Now I'm going to do the same thing with this box. Either your marbles or Bunny's marbles are going to go in this box. Alright, are you ready to do the shaking and listening? Okay, so remember, over here, there's either your...
It's a little slow.
Okay, let's listen. Alright, and over here, there's either your marbles or Bunny's marbles. Let's listen. let's do it one more time.
We'll skip the one more time for the benefit of the adults and just say, sorry. But if we ask the child to choose, she goes ahead and chooses the box with the more discriminable, more informative evidence. And kids are astonishingly good at this. Across a bunch of studies, you can show that the kids are sensitive to both after they hear the box, but even before they hear the box. They can tell you which one they want to go ahead and choose. So preschoolers know when evidence is more or less distinguishable. They may have this kind of intuitive psychophysics where they're sensitive to the thresholds they can discriminate, and they prefer interventions that generate distinctive patterns of evidence and so maximize the probability of information gain. Is that clear? Okay, so that's the end of the sort of main and first part of the talk, where mainly what I just want to suggest is that our abilities to gain information and to generate informative evidence, even in very young children, turns out to be very sophisticated in a bunch of ways. And I think it's a challenge for our modeling approaches and also for our neuroscience to understand how these kinds of representations are implemented.
Why
Yeah.
did they choose the box even if you didn't shake it?
Oh, because you can ask them you can tell them what you're going to do. So you're going to say, well, we're going to shake one of these boxes. Now you don't know what you're going to hear, but you can ask them in the case where. Whoop.
But if it was the bunnies, then in one of the boxes, they wouldn't have heard anything. So that could have been informative information and the marbles were not there. So the shaking is useful, right?
Sorry. So if you take this case is a little bit simpler, but if you take a case where you tell the kids, okay, well, we want a shiny pencil, and either this or this is going to go into the box, or this is going to go into the box, and we're going to shake it for you. Which box do you want to go ahead and actually, you know what? This is brand new research, and I can't remember the question they asked. They asked an anticipatory question about what kind of evidence they wanted to discriminate. And the kids preferred the case where they had the more discriminable data, but I actually can't remember the structure of the question. If they did something like shake the boxes, but they didn't. They did do it before the kids heard the evidence. So I'll have to get back to you actually and remember exactly how they structured the question. Celeste.
Which one do they want to search? So Julian just told me about the study.
Was it which one they want to search?
The question where it was before is which box do you want to search? And they know that they'll have an easier time searching when they're discriminable versus not.
Thank goodness someone's heard my graduate students give this talk more recently. I want to go on and ask this question here, which is whether exploratory behavior is related to intelligence, and especially individual differences in exploratory behavior. 2 minutes? Okay. In that case, I'm gonna flip through very quickly because again, this is very new data. But we know already that rates of habituation in infancy are better predictors of IQ than basically anything else. And rates of habituation is just basically how quickly a baby gets bored looking at the same stimulus over and over again. And disorders of exploration seem to characterize some clinical diagnoses, but we don't really have, it's not like a vocabulary checklist or something where we know what normal milestones are for exploration. So we started to ask whether we could look at exploratory behavior in 6, 9, 12, and 18-month-old babies and predict longer-term outcomes, in this case IQ at 3. So in the interest of time, I'm going to just tell you that we ran a battery of measures, and then at 2 we looked at whether there was any correlation in any of these measures with the kids' vocabulary score. And the only one that was significant, was exploration. And that motivated us then. So this was obviously, we didn't know, we were searching. So it was a bit of a fishing expedition. And so we needed to constrain our actual prediction for the 3-year-olds. So at this point, we said, okay, we're just going to use the exploration measure, and we're going to see whether the exploration measure predicts their IQ a year later when we can actually get it. So the kids played with just off-the-shelf toys like this. They were allowed to explore as long as they wanted, up to 5 minutes. And the measure that we're using here is not just how long they explored, but how many parts of the toy they discovered. We'd pre-specified the parts of the toy given the amount of time they played. So it's something like the efficiency of exploration. Now, actually, the number of parts they discovered should fall off with time. It's harder to discover parts after you've discovered the first few. So this is a conservative estimate of how efficiently the babies are exploring. This is the phase 2 measure, and you'll see the other measures didn't predict anything about their vocabulary. So when they were 3, they went to a different lab and that wasn't involved in the earlier parts of the study, and they got IQ tests, and there's a measure in preterm babies, but the exploration measure also distinguished our at-risk sample from the not at-risk sample and the 2-year-old measure. But what I want to show you is the results at age 3. And what you'll see is this is true both of the first visit, and they had 4 visits, and their mean exploration. And the efficiency of babies' exploration correlates with their full-scale IQ when they're 3 years old. Yeah.
Does it hold even without the outliers?
Yes, it holds without the outliers. I do want you to notice something. This is a 3-year study and a longitudinal study, and these are very high IQ kids. So although we started with an at-risk sample, most of those kids didn't stay in the sample. There were multiple at risk and an early intervention. So the kids who are in our sample, it's predicting the IQ of extremely bright kids, a range from about 100 to 140. So obviously we need to be cautious about how we want to interpret the results. The bigger problem, I think, is that we don't know why. We don't think it's motor skills because many of these tasks called on motor skills. It could be something about the ability just to engage and disengage attention. Obviously, we're interested in whether it has something to do with this ability, the ability to actually recognize when you have should move on, when you're optimizing information gain. But of course, it's a correlational study, so it's even possible that efficient exploration in some ways makes you smarter and supports intelligence. So there's a lot we don't know from this study, but there's some preliminary data right there. I'm going to end with a last point that Jacqueline also made, which is there's a lot to behavior that it's a little hard to capture with these models. So I want to return back out to the actual world of play. In this task, children had to figure out which gear was making the other gear go. And I just want to show you that there's a lot of real behavior that we don't really capture here, right? Sometimes the kids generate informative interventions, but in a kind of chaotic manner.
I can hear it inside. But it's way louder and sillier.
Okay, so these are the things you can't predict. And in some sense, that's what makes play, right? This richness and this diversity. But it's a little bit troublesome. We try to shoehorn it into really elegant models that say a lot. But there's a lot we're not saying. And you see it both in richness, but you also see it, and Celeste mentioned this too, in things that look like stickiness, but don't really look like they're about inhibitory control problems. So this is an exceptionally cute baby. This is my daughter. And when she was, 14 months here, she really, really liked to do this. She did this thing where she sort of sorted and made groups with acorns in the field, with blocks, with anything she could find. It lasted about 6 weeks. I'm a professional developmental psychologist. It happened all the time. It was very marked, and then it went away. And I don't know what she was doing. And I don't know that I will ever know what she was doing. The important point I want you to notice about this video is primarily that she didn't exhaust. I got tired of filming her. She went on for 20 minutes. And it's basically the same thing. She's not discouraged when it doesn't stay up. She's not particularly sucking. And I don't know why. And this, I think, is the tip of a giant iceberg. Human beings do a lot of things, right? Yeah. We want to cure cancer. We want to understand how the mind works. We want to understand the behavior of New Caledonian crows. We want to win hot dog a word eating contest. And I think there is a puzzle here about if we're just sensitive to information gain, if fundamentally evolution has the day and just cares about how many grandchildren we have, what are we doing? What are we doing with all of this? Is it just a side effect of intelligence? Why are we curious about so many different kinds of things? I've been puzzled about this a lot, and I've been puzzled about it, and especially in relation to what I think is a deep problem of human cognition, which is that we don't just learn from data, we learn from just thinking, right? Very often we generate new hypotheses by sitting around and making them up. Or because someone poses a problem and says, hey, why does salt raise your blood pressure? And you can make something up even if you're not a doctor, right? Or what would be a good name for a new theater company? You could all think about it and just generate a response on the fly. And I could go on all day throwing questions at you, and you would come up with answers that might be wrong, but at least they would be wrong. They wouldn't be incoherent, they wouldn't be irrelevant, they would be within that hypothesis space. And that turns out to be a very hard, as I'm sure folks in machine learning know, it's a real question. How do you do it from just thinking? And one of the things that seems true is that thinking is often thinking about a problem or a goal, and we know a lot about our problems before we solve them. We know what a good answer would look like. We know when we're getting closer. We have some sense of progress towards a goal, which is a bit of a puzzle since we, by definition, don't know the right answer. We're not better predicting the world at that stage. Nonetheless, we think we're getting closer. There are ideas that we know are wrong that we can describe as elegant ideas, right? Elegant in virtue of what? They've been falsified. They don't predict the world. We still think they're good ideas. There are other ideas we think are bad ideas out of hand before we've tested them. Again, in virtue of what do we know? And one of the things we've been toying with is the idea that problems and goals act as constraints on hypothesis generation. I've been doing this a little bit in sort of a live debate. Sorry for all the text coming up at once. I was just adding it. But Tomer Ullman, Noah Goodman, Josh Tenenbaum, and I have been working this problem together, but we staged it as a debate. And they've proposed a model of stochastic search where you basically start with some hypotheses about the world, you propose small changes at random, and then you keep testing and getting them right. But the problem is this is very, very inefficient. It can make proposals that are tautologies, that go in loops, that are circles. Machine learning algorithms get stuck for a long time doing this. And humans don't seem to get stuck in this way. And so one argument is, although we can have innumerable goals, each goal can only be solved in a very limited way. Our goals and our problems might constrain the search space because they provide criteria for their own fulfillment. So if we take the information in the problems that we pose as information, say the problem has a particular form, we know one thing goes up and another thing goes up, so we're looking for things like that. That could help for learning. And in this sense, it doesn't really matter what the content of our goals is, as much as that it's a goal and it constrains the search space. So sometimes we have goals that get obsolete over time. Analytic logic was developed by monks looking for incontrovertible proof of the existence of God, right? But the fact of having a goal, which required things like infallibility and provability, acted as a constraint on the kinds of ideas that were generated. And so one possibility is that the diversity of goals is there because it actually helps constrain our learning quite broadly. So that's the end, and thank you very much.
Questions? Maybe I will begin by.
Yes.
We've seen in the last video with the kids not only playing with the object they're trying to discover, but playing together, that social interaction may interact very importantly with the mechanisms of exploration. In that case, we can get the intuition that in this context, social interaction is fostering exploration, and they might discover more efficiently things about the object. But then, in some other contexts, like for example, being a little kid in front of a big scientist trying to observe what you're doing, then the effect of having a social peer in front of you might actually limit or in the expression of exploration. So is this something you've tried to look at or think about? Like, first of all, how the interaction is working, and then how you can control for this in the experiments you do?
Well, in the actual experiments I do, I never use dyads, right? So you always saw, those were outtakes from pilot work. And we always looked at a single child because it's just too hard to code behavior.
The experiments have the scientist looking at the child.
Yeah, so I think social interaction is hugely important. Actually, most of the work I've been doing for the past 3 years isn't this. Most of it's focused on learning in a social context. We know things like, for instance, that teaching constrains exploration. If you instruct someone and say, this is how my look at my toy, and show them anything about it, they explore less, right? Because if there were other properties and you're the expert, you should have shown them to them. So there's a good inductive bias that trades off instruction and exploration. What you do with another peer, of course, there's, like both of you can't grab the same toy at once, so you're going to generate more variability. There's a lot of questions about what happens in these contexts, and I think a lot depends on the particular structure of the context. So we know that children, for instance, will present more information if they think that a peer, in this case Elmo, wants to know how a toy works than if they just want to make the toy go. So if Elmo wants to make the toy go, the children will take low-cost actions that are effective. But if Elmo wants to know how the toy works and to isolate the variables, you have to walk across the room and do this. They will do that in a teaching context, but they won't do it in a just showing context. That's sort of teaching to another. It's not joint or cooperative play, but it's starting to ask those questions at least.
Other question? Everyone's beginning to be very tired. So just actually a second one on your, one of the perspectives you're giving about goals at the end, basically saying that activities or goals would be interesting if you can figure out a good measure of your progress in a way.
Mm-hmm. Mm-hmm.
Have you been trying to explore this idea experimentally? Like for example, I don't know, like imagining like the kids have the choice to explore various kinds of complicated objects, but then for some of them it's not really clear how they can measure if they are understanding or not, as compared to another one.
We haven't asked that question, although I think the fact that we have intuitions about things like tractability and progress is an interesting problem. I think there's also a different case in the case where you know the goal, you want to get the food inside, or you want to make the toy go, you just don't know how to do it. Then the hard case of thinking of new ideas, where sort of roughly, I would like to understand learning, right? But you don't really know anything more about the goal. And I think actually when you have those sort of ill-posed problems, you can't make progress, right? So you actually do need to have goals that sort of define the criteria for their solution, so you can tell, so you can learn. I think that's an important point. So what we've done experimentally is things like give kids no data and two things that are consistent with prior knowledge, right? So here's an affordance, it goes like this. Here's something that goes like that. You can take a peg out of a hole and put it in another hole. You can take a bead like this. And here's a display. And the display either has a light that goes up from the top to the bottom, or maybe a sound that goes on and off, or something like that. And we just say, well, how does it work, right? And the kids will do a mapping from a continuous cause to a continuous effect, which suggests that they don't know and everything's consistent with prior knowledge, but if the goal is to explain this, they can do some kind of analogical mapping just from the causes to the goals. It's not a classic analogy, right, where you know this problem has the solution and this one does, but it's a representation of what would count as a solution because it has the right form of the problem. If you ask them a different question about the same stimuli, like how do you change a continuous light to a continuous sound, they'll choose a discrete cause because you're changing modality. So it's not just cross-modal mapping, it's something about representing the kind of problem you have and what would count as a solution. And again, in all cases, there's no covariation data and there's no difference in prior knowledge. It's just the abstract structure, the form of the problem that constrains the form of the solution. So that's a start. But I actually think this is a problem for AI and machine learning and computational cognitive science, because the difference between hypothesis generation and generating a whole billion hypotheses and rejecting them very, very quickly versus generating constrained hypotheses very efficiently isn't something you're going to tease apart empirically. The only way I can think of to tease it apart is to develop a model that does the latter instead of the former. If we could figure out how those abstract constraints could constrain the generation of hypotheses and show that it does better. Yeah.
Yeah,
For a while, recently I've been interested in, there's this whole literature in adult cognitive psychology on hypothesis generation and hypothesis evaluation, and some of the models that I've encountered start from the assumption that you basically have a whole bunch of hypotheses stored in memory, and when you're trying to evaluate you get some new data and you're trying to evaluate hypothesis for that new data, you're basically computing some kind of similarity. It's basically based on an exemplar model of memory, so you basically compare your data to all the stored exemplars that you have in memory, and you come up with a hypothesis. And I think it always struck me that seemed that sort of model would only occur to someone if they were thinking about very strongly constrained hypothesis spaces where you don't need any kind of creativity. You don't need to solve problems where you're doing like any complex analysis of the problem, like the means ends and analyses, for example. And so it just reinforces this impression that like that whole line of research should be sort of revisited from the perspective of more complex hypothesis spaces.
One of the things that's always been intriguing to me is it's trivially easy for us to generate hypotheses, right? Like I say, you could, Sam and I have joked in the past, but you could imagine we have a BS generator, right? You can ask anybody anything and they can make up an answer for it. And in some sense that looks like a foolish aspect of human cognition. But if you imagine that we actually have to do two things, we have to generate hypotheses and then we have to find out if they're true and if they better predict the data and they predict the world. If you're going to go beyond the data, you actually need a bit of a firewall between your testing things and the things that will let you generate ideas that, if they were true, would solve the problem. And we're very good at generating the ideas that, if true, would solve problems. And arguably a lot of what we do when we're daydreaming or imagining or worry, or the fact that this is so characteristic of early childhood, that they set up little problems and they solve them, and set up little problems and solve them. Those problems have no bearing on the real world. They don't better predict things. Probably, children's pretend play is not good training for being a parent, or any of the other things that they're playing. But it is very good at setting up small problems and solutions, small problem solutions, and learning how to make a fit between sort of abstract constraints and something that, if it were true, if you could realize it, if you could do it, would work. And then you can go back and find out, well, can I? Is it feasible? Is it practical? Is it accurate? Is it do a better job? And so the way I've been thinking about it is two quite separate processes. One of what Stephen Colbert called truthiness, getting things that are sort of sound good, and then another of getting it right.
Yeah, and actually, like there might be some methodological ideas from that literature that I just mentioned, where I don't know how easy this kind of thing is to do in children, but they explicitly separate these two stages where they ask people to generate hypotheses and then evaluate their probability. Actually, Liz Bonowitz did studies with Tom Griffiths, a few studies like this, where you have these separate generation and evaluation phase. But it would be interesting if you could sort of explore, in some kind of larger scale way, explore the sort of manifold of data and hypotheses that are generated from the data, so you could start to understand, like, for a large variety of data, different data types, what sort of hypotheses do children or adults generate?
Again, the best I can do is think that there's information in problems. One thing that's also striking is we have like 5 question words, right? Why, when, where, how, what. That's a very small set of words for carving up any question you may ask. But those questions contain information. If you ask when, the answer's got to be a timeline. If you ask where, it's going to be a map. If you ask, what, some sort of concept space. If it's how, it's some sort of circuit diagram. Why is some sort of tree structure. You know a lot about the representation, even before you know what I've asked about. Right, just by posing a problem. So by taking the problem as input to how you find the solution, you could constrain a very large search space somewhat efficiently. You would still eventually have to do all kinds of other kinds of learning in stochastic search, but at least you could narrow the space over which you had to do stochastic search.
It's interesting because the problem that you're posing, a real one, is at ontogenetic level something very similar to a problem of philosophy of science, of epistemology. I remember in the early days of optimal foraging theory, when people said, we assume that we can predict the behavior of organisms on the basis of maximizing evolutionary success. There were serious opponents to that said that the approach was intrinsically flawed. There were many reasons, but the main one was that it very often failed to predict. And people who defended it, I remember being in Brown University once in a big debate about it. The main defenders of the approach said, oh, but it has led to a proliferation of studies. There were many studies thanks to testing this particular field. And then the people against it said, well, you justify it because it gets you a job, because you're actually pulling the wool in front of the eyes of the fund givers. And then they give you money, and then you publish lots of papers, but they are not good. But the truth is, we didn't know how it would work without a framework of things to test. So we needed goals of this kind. And a similar case in other domains is, I had a conversation with a forensic psychiatrist who had worked for many years with Massachusetts police, actually, to try to identify the psychiatric profile of a serial killer that was suspected to exist over something like 20 years, uncaught. And I asked this person whether you see that in films very often, right? The ball film that actually helps the police. And they said, has it ever worked? Has it anybody made a capture of a perpetrator on the basis of that? And he said, oh no, not to my knowledge. And I said, what's good then of doing these psychological profiles and having the maps with saying where the killer, all these kind of things? And he said, it calms the anxiety of the police. It gives them something to do so that they can keep going. So they have hypotheses, and then in the course of testing different things, oh, maybe he's a psychopath of this, maybe he has an obsession with horses or whatever. And so they keep going. If they didn't have that, then they wouldn't have any energy to keep attacking the problem. So it's rather unambitious, but it's still a goal for
What's the point of attacking the problem if they didn't lead to finding the serial killer?
Well, eventually they found it, right?
No, as far as I know.
But sometimes they find it. Oh, right.
It may not exist. The guy may not exist. It may be that the different crimes are not a serial killer.
It's the latent cause. They assume the stochasticity is due to latent.
I think. Oh, go ahead.
Yeah. So this.
I don't know the answer.
I mean, this is actually what I'm most interested in right now. But
But it gets to the idea of motivation, and it gets to the question that Pierre asked before. So what's the point of looking at good things, Pavlovian things that are uninformative? And the point is that it makes us feel good. Right? It makes us feel good or motivated.
But that
in your
can't be a
case.
selective advantage.
Well, maybe. So there's the theory. I don't know if I only heard of it. There's this theory of positive psychology, right? I mean, it's possible that when we're in a better mood,
actually, it's.
Associative thinking becomes.
I think it's better than that.
Generation becomes facilitated, and your thoughts are more fluent. You just think better.
That may also be true. I just heard Tali, and I'm going to forget her last name, give a talk at MIT on a positivity bias in humans, which is very marked. You're roughly Bayesian when you have good news.
I meant more the positive psychology, but I know what you're talking about.
But one possibility of why you need to do that, or why you need to selectively update for good evidence, is that if you're going to do long-range planning of any kind, you're mostly going to fail, right? So.
And that's actually like in reinforcement learning theory. That when people try to design systems that do something like hierarchical reinforcement learning, they very often need to use what they call a shaping function that basically gives a kind of surrogate reward. It's a fictional reward that will encourage
you have to have a lot of tolerance for bad news compared to for any kind of structured, because mostly think you're going to build a bridge, it's going to be a mess for a long time, then it's going to work. So for any sophisticated long-range test, failure is going to happen for a long time, including for the cockatoos.
Yeah, so I meant this more in terms of in terms of regulating global state, and maybe there is a global state that is induced by things like humor and laughter, and maybe it facilitates hypothesis generating, maybe it facilitates associative interactions. I mean, I think there's evidence that, for example, in depression, the thought narrows. and there's rumination, and you just so
But then
free,
you have to
free
explain
association
why.
tests are really impaired.
But if that's the evolutionary argument, then it just sort of pushes the burden onto why that evolved. Why do you have this positive thinking effects on fluency and associative thinking and so on? Why would that evolve?
Well, it's just there, and then that turned out to be beneficial because you generate hypotheses and figure things out.
But why is the information processing system designed in such a way that being in a good mood causes you to, like, what is
Well,
the,
in general, right? So maybe it comes from just seeking rewards, right? If you see a reward, you want to get activated and motivated and energized.
But you might want to,
And
in that
then-
case, you want to
and your
might want to be
thinking may
thinking
want-
even more
Yeah.
narrowly, right? If you see a reward, you don't
Yeah.
want to be distracted by other things, right?
Right. Okay. I don't know.
Okay, so
I don't know everything.
I mean, it's all just those sort of things.
I only know.
Mike.
last question, and then we will have the break.
Okay. Well, this gets at a bit of what we had talked about earlier, but so you're mentioning that the system that really good at doing BS, and so in terms of the question of why would you engage in goals and hypothesis testing when it's not useful for any immediate reward? In order to satisfy some goal, you need to maintain it in some kind of form that then allows you to filter out the relevant sub-goals, the relevant aspects of the world that you should focus on in order to achieve your sub-goals, and then, compare having obtained that sub-goal to your larger goal, then sequence it to go to the next sub-goal, and then, finally you get to the actual goal. And in order to do that generally, you might need to train up some machinery that you can practice using sort of a general purpose machine that allows you to filter out irrelevant information, to make the world more Markovian, to use working memory in a good way that would then be useful for all sorts of things. And so I think, it depends on the hypothesis that there is a kind of general purpose machinery that you can practice and then use it for other things. But I think that's actually, there are some mechanisms that people have proposed for that.
For hypothesis.
I think that the important point about goals is Reverend Bayes did not predict any of this, right? Like when the kinds of ideas we come up with under the particular motivations we come up with them are basically lost to the species. What's retained is the ideas of the plan. So who knows? They didn't catch the serial killer. This guy's work was completely wasted, right? Except that in 50 years, somebody goes back and looks at that paper and say, hey, this is an excellent model for and does something with it, right? So you can have ideas and motivations that are venal or trivial or misguided or don't work, and it turns out maybe not to matter because the products of those, the degree to which they generate information is basically independent in some, maybe not totally independent, but certainly not very closely linked with your motivation. We come up with ideas to impress people or because we have grant deadlines or conference deadlines, right? And that may be our motivational structure. It may not matter very much. We know the constraints of a particular form. We know we have to do it in this kind of way. Those constraints support learning.
Like your kid, why would they engage in this goal that you don't know what it's for? And I'm saying that it's useful to have that because you're going to practice the machinery that allows you to do it more generally. That's going to help you in other situations.
I think that the problem is that we may fail in goal identification. It may be that actually it is working for something and we are misidentifying what it is for. For example, it could be that these kids are working on establishing a bond or at establishing dominance or practicing who initiates an activity with respect to the other. There are lots of things that could be the goal of the interaction, and we think it is actually the control of the machine, but actually that's not the benefit. So there may be a very clear benefit. In the case of the forensic scientist, for example, that's different because the social organization may be irrational. But one could argue that if it keeps the police brains active, then you keep a police force that actually might detect other crimes or whatever. So the problem we have is that we define the narrow goal in a way that may be mistaken. I mean, animal behavior is very often the case that you see them engaging in some behavior that actually is ritualistically helping the animal establishing dominance or something like that. It's not what it seems to be about.
Okay, so Thank you.